Hello, everyone. Just a few more minutes. We'll be right there. Back up.
Hello.
So we are we're gonna start in a few minutes, and we'll have a whole hour. So those of you who just joined, welcome to the webinar. Nice to see you. Hi, Peter. I see Peter is here as well. Okay, yeah, should be a very interesting and fun webinar today. Thank you, Ulrich, for agreeing to speak today.
Hello.
So Ulrich, are you back in the office, and Pekka, you're all? It looks like you're not in the office, but
I'm working on distance today.
Yeah, That's what we do too.
Yeah,
hybrid work in a sense. Yeah.
Back in the office, but we are expecting to return back home.
Yeah, I saw that. Yeah, I saw the cases.
Numbers are increasing rapidly, and not sure in Finland. Is it also like that, or?
I didn't listen.
I said we are in the office currently, but we probably are moving back to home office in a few weeks from now, because the numbers are increasing.
That's possible. I just received email from the university that all these big public events will be closed from today.
Exactly.
So same trend here.
Shutting down.
Okay, so it's 9 o'clock. We're going to start in a few seconds. Everyone is aware this is going to be live streamed on YouTube as well. So those of you who are watching on YouTube, hello. I know we have a couple of folks watching there as well. And yeah, so excited. So we can get started in a moment. So hello, everyone. My name is Markus Bühler. I'm the editor-in-chief for JMBBM, and I'd like to welcome you to today's JMBBM Frontiers webinar. This is our second webinar this fall, 21. And I'm very excited today that we have Professor Ulrich Lohbauer as a speaker. He's also one of our newest editorial board members. And so one of the first assignments he got was to give a talk today. I'm very happy that he can do that. And our moderator today for the talk is Pekka Velitu, who is one of our associate editors, of course. You know him. And so in a moment, I'll be handing it over to Pekka. He will be moderating a session. A few things on housekeeping. We'll be taking questions after Ulrich's talk. And I think he'll speak for about 45 minutes or so. You can put your questions in the chat or in the Q&A. So we're very flexible today in how we get the questions. If you're on YouTube, the same thing. You can put it in the chat on YouTube, and I will be passing them on to the speaker and the moderator during the Q&A session. With that, I want to welcome you all again, and nice to see a great audience today. Very excited. And with that, I'm going to hand it over to Pekka. Thank you.
So good morning, and thank you, Markus. It's my pleasure to chair this webinar, JMBBM webinar of our journal. We have had very interesting ones, but as far, this is the first one purely on dental materials, if I have understood correctly from the abstract given by our presenter, Lohbauer. So our webinar presenter is Professor Ulrich Lohbauer from University of Erlangen-Nuremberg from Germany. He is presently one of the key scientists in the field of dental materials globally. He has long-lasting experience to work with the most well-known biomaterial scientists. For instance, Larry Hens, in earlier time when Uli was visiting scientist in London. So he's certainly having very strong background, not only the dental materials, but to the materials in general, and especially the brittle materials. And then as his presentation will be entitled of fractographic features, how materials can and will fail in clinical or in vitro conditions. So by these words, I'm very eager to hear what Ulrich is going to tell about fractographic approach in dental biomaterial research. And then I give this virtual audience to you. And then as said by Markus, we are ready to discuss about this topic by your questions after the presentation, which will be then covered hopefully in detail. So Ulrich, audience is yours, please.
Thank you. Thank you, Pekka. Thank you, Markus, for the kind invitation to give this webinar today, and for congratulations for the webinar series, JMBBM webinar series that you organized. I think this is a very nice initiative to extend the focus of JMBBM. Thank you, Pekka, for the kind words, for the introduction. And so I don't need to introduce myself. I just share my screen and hope you can see the presentation. I selected this topic, the fractographic approach in dental biomaterials research, because I mean, fractography is a tool that is probably known to everybody who is in biomedical or mechanical biomedical engineering. And I will present on dental biomaterials as this is my expertise, but fractography is certainly a tool that can be extended and applied to any time of biomedical material, and especially in mechanical engineering. This is a very, very useful tool that should be incorporated in any type of mechanical testing of material tissue combinations. So I will start the seminar with apologies to Morgan Freeman. Sorry, Morgan, if you listen to this webinar, I took your example as a very nice example to show people the dental situation before and after aesthetic modifications. I mean, this is certainly a decision of aesthetic experience and improving the appearance of an individual, but from a scientific standpoint, this is extremely interesting for any type of research into mechanical biomaterials engineering, and requests a lot of skills from the practitioner, from the dental practitioner, to really modify the dentition as it looks like on the right image. So this is very interesting. And of course, a patient pays a lot for such a treatment and wants to receive in turn a long-lasting restorative situation. So what are we normally doing as engineers is that we look in the daily dental practice, we look what is happening in the field outside. On my side, sitting in an in vitro, in an experimental lab in a university environment, I don't get so much feedback from dental practitioners. So we actually rely on clinical studies, the highest level of evidence, prospective and controlled clinical studies where variables are narrowed down and the situation and the performance of materials in the mouth, in the dentition, in the occlusal situation between the upper and the lower jaw is really tested under in vivo conditions. So, but in order to further standardize, we go to bench tests, we go to simplified bench tests, ending actually with very simplified models in which we perform ISO tests or very simple tests that gives us an idea about a material performance that we can use later on to recommend the manufacturers of dental materials, to recommend the clinical treatment procedures, and also to indicate materials for certain loading situations in the oral environment. So in the end, we are providing dentists with charts like this. This is an Ashby chart. On the left side, combining the strength with the toughness, and you see the increase in strength and toughness from the bottom left to the upper right. And we can select the window here. This is a very small window that we can use in dentistry with reinforced unorganic material, glasses, glassy veneers, or glass ceramic materials. We can also use highly filled polymers, metacrylic polymers, or on the upper end of toughness and strength, also zirconia. Here is zirconia or alumina. These are the major materials from a mechanical perspective, and also, of course, from an aesthetic perspective. We cannot certainly use silicon nitride or another material that offers a different aesthetic appearance. So, but how does a dentist really use this information? Can he treat a patient by knowing the strength or the toughness of a material? And this is an example how things should not, but in reality could end. So this is a restoration. This is a single tooth crown here that fractured in the middle. And if we have in mind, assuming let's have the example of the US, we are having 200,000 dentists in the US. Every dentist does a crown a day, so they are working 200 days a year. We have more than 50 million crowns in the US. So this is almost 40 billion US dollars that are spent on single tooth crowns. If 1%, only 1% fails due to fracture, this is a really economic issue, not only a treatment issue for the patient. So, but what can we do? We have on the one side, from our providence to the dentist, we have hard material data. And on the other side, we have the clinical situation that crowns are long lasting, or they are failing, or whatever, how they perform in the mouth. So we need to find a way to learn from the clinical situation, to learn from the fractographic evidence, just looking at those fractured crowns and the fractured surfaces. And then we can specifically recommend procedures or materials for the clinical success. I call that somehow the yin and yang between construction and design on the one side and destruction and defects on the other side. So we need to learn from the failures in order to recommend to the clinicians how to improve their treatment procedures. This is actually the way how fractography comes into the game. This is actually a tool. This is not a scientific a field or approach. It's very simple. Many people have already made experience with fractography, so it's very easy to see this mobile phone that dropped and fell down on the floor, and the origin of fracture is somewhere up in this corner. So it's very easy to perform fractography, no tools, no specific microscopes needed, just simple visualization of the fractal event. This is a glass window that has a bullet has touched the window, and it also here it's very easy to locate the region of fracture origin. That can be maybe be more complicated once the material is more resistant and there is stress coming into the game. So this is a strengthened glass window, and it's easy to locate the fracture origin, but we can see some regular patterns. We can see this forking here. We can see these features. So these are repetitive features that we can identify on a fracture surface. And we are able to conclude on the stress level in the material, the residual stress level, either low stress or with higher forking incidents, we can conclude on higher stresses. This is very well known in engineering and glass engineering. So the branching angle, especially in bottle industry, pressurized bottles, this is a really scientific issue. And it's not only depending on the ratio between stresses from different direction, it's also depending on the direction of the impact, or direction of the fracture event, and we can conclude on the history of the fracture, hopefully to prevent any type of fracture for the future. Fractography is not a tool invented in dentistry, but to give you an idea about the length scale, there is kind of rock slide that happened 10 years ago in the Swiss Alps. So there are people in science who really do fractography on such events like a whole rock slide. Of course, they don't use a microscope to investigate the fracture surface, but they have different methods and they also perform the same principles. For us in dentistry, it's much more microscopic, and we need to narrow down the window. This is an intraoral mirror that you can see. This is an inlay restoration. So here is the margin of the inlay restoration, and this piece here fractured off. And we can, of course, retain the fracture after cleaning. We can put it to the microscope. We can investigate. We can see the surfaces, and then we can magnify and in the end conclude on the fracture origin on the one side and on the reasons for fracture on the other side. All right, this is introduction to fractography. Why is it necessary for us in biomaterials research? And a quick one here to show you what is the typical way to approach our scaled surfaces. We use a light microscope, for example, a stereo light microscope that gives you three-dimensional impression of the surface, which becomes more and more important, three-dimensionality of the surface. You can also use a digital microscope that creates a mesh over the fractured surface, and you can three-dimensionally analyze the surface. But this is the most common tool. There's a light source. It's very important for us in dentistry to have lateral illumination, because we have translucent materials and we can see cracks from the side. This is very important to handle those light sources. We have a camera. We can record our images, and of course we have a magnification which does not need the highest one that is available. A medium magnification is wonderful to see and analyze on surfaces. If there are details that need more magnification, we go to the SEM or different other techniques, but this is very nice for the first approach. More important is also the treatment of specimens. So holders, for example, how to put it under the objective in order to rotate and to find the right angle of illumination, to play with the surface, to see the contrast. This is very important. There's a pen that can be used in order to increase the contrast on the surface, to paint the surface and to see the contrast. And of course, there is a huge field of cleaning surfaces. I come to this point at the very end when I describe much more useful tools for fractography, but cleaning is essential. When we are looking at clinical specimens, we always retrieve those specimens from an oral environment, or there are contamination with saliva or blood or any other type of contaminations that actually cover our fracture features on ceramics or on brittle surfaces, and we need to remove those debris before we can see the surface and before we can investigate the surface. But for cleaning, there's a bit more at the end of the talk. So very simple. It's not mine. This is from George Quinn. This is a glass rod, but it has such a nice fracture origin that I have to show you this example. This is a glass rod that is fractured in 3-point bending, and you can see very easily see the fracture origin at the bottom side, where is the highest tensile stress and where it should be located. So this is again the same fracture origin, and we can see or identify. This can easily be done with a light microscope. The origin of a fracture, the fracture mirror, this smooth surface, very flat and smooth surface. Then there is a mist region where the energy of the crack and the velocity of the crack is increasing. And then we have a coarse mist and the hackle region where the energy is even more increasing and the direction of fracture planes are inclining, and those hackle and coarse regions are developing by moving away from the origin. But anyway, tracing back those features brings us to the point of the fracture origin, and we can easily locate the reasons for failure. So this can also be measured. There is also a relation. That relation can be further investigated with Irvine's law on fracture toughness, or the strength of a material is related to the crack size, and the constant is the fracture toughness. So we can actually perform quantitative fractography on fractured surfaces. It's not always that easy to see such a fracture origin in coarse grained ceramics, for example. It is more difficult, and we can maybe, needs a bit of a training and also a bit of a distance to the object. We can also see the limitation or the borders of the fracture mirror. And on some point, we can identify different fracture mirrors, which give us an gives us an indication of fatigue degradation going on, crack extension going on. So this type of extension is also very valid for investigations on degradation or fatigue failures. There are examples, most of them in glass, but these are typical examples which we can find on a brittle surface, like ceramic or even filled polymers. So the most easiest is always the compression curl, which is on the opposite end of the fracture mirror. And this is actually an inclination of the fracture plane when it comes under compressive loading. So the compression curl is in most cases found, and we need to see or seek for the fracture origin in the opposite direction. The fracture mirror is very typical. Hackle in any type of shape, so a coarse hackle, a twist hackle, wake hackle, developing after a pore when the planes are meeting again. These are very typical fracture features. They guide us actually towards the fracture origin in this direction. Actually, there are arrest lines when crack velocities change. There are Wallner lines on surfaces, dull wings, contact, edge chips, or some more specific types of here Hertzian cone cracks, for example, which is common in dentistry when we are under occlusal loading. So these are very typical types, and we can use it to really trace back the fracture event to the fracture origin. If you wish to learn more about fractography of brittle materials, fractography of ceramics and glasses, I highly recommend this book here. You can either search on Google NIST George Quinn fractography. You can find the download link. It's for free. And this is the 3rd edition, so that came up this year. So I highly recommend you to download this publication, this book. This is actually the most comprehensive one that we can find for fractography. All right, some things about how to investigate and how to see and how to investigate on a fracture plane. But how should we use it in analysis? How should we use fractography as a tool for our specific research? So it's probably depending on the material, on the level of inspection. So there's probably a visual level, there's a more specific microscopic level, and that can be extended further down to SEM and TEM structures, and also the analytic level that we assist our findings with modeling, stress analysis, especially for us in dentistry when we are working with bilayer or multi-layer structures. Think of a crown that is that has a strong zirconia core and that is veneered with a weaker porcelain material. We can also analyze the chemical composition to see heterogeneities in the material, and quantitative calculations through the fracture toughness. FE modeling, everything's possible. So the question is always for what you wish to use fractography. So in some point, it's enough to use the visual level to see the failure reasons, to identify the clinical failure reasons. For example, in dentistry, we are having the problem that the surfaces are grinded during insertion of the restoration, and this grinding induces defects, and this is kind of failure reason that is easily identified on such a surface. So we can use it for recommendations, we can use it in construction design, but we can also use it to see what's wrong clinically. We can use it for us how to develop specific preclinical testing protocols that are really clinically relevant and that are not like the simple ISO tests providing data, so that they are more related to the clinical reality. On the microscopic level, we can see the microstructure. We can identify processing defects in a material. We can engineer and improve the microstructure of a material, and we can also conclude on longevity, on degradation of materials. This is all possible when we increase the microscopic level. In the analytical level, we go down to material science, structural development, and improving also the processing conditions of materials, for example. I'll give you some examples that are very prominent in dentistry, but also in other fields. So this is a Weibull graph of strength distribution of a material. And this Weibull statistic, they provide us with a certain characteristic strength at failure probability of 36%, and also the scatter of data, the homogeneity, the Weibull modulus on the measurement of 20-30 specimens that we use. But we can go much further once we analyze every single fractured surface. And we can say, okay, the fracture is emanating from a processing defect at the edge, for example, an internal microstructural defect, a surface defect, a processing defect. This is, everything's possible. So we can identify, or we can separate the reasons for failure emanating from the processing of the material or emanating from the microstructure. This is very helpful in material development, but we can even go further to clinical fractography, and this is one of my first cases that is also in Journal Mechanical Behavior of Biomedical Materials. That is actually a 6-unit prosthesis, anterior prosthesis that fractured on the first day. Here's the fracture. And we are able to analyze visually. We can see the core material. We can see the Veneering, the veneering material. We see a huge pore inside the veneering material. And we can certainly already conclude there is something wrong in the design. So there's a different design. There's a different anatomical design of the core. On this picture already, you see the exposed white Zirconia core material and the yellowish or tooth-colored veneering porcelain on top of the Zirconia. When we further go down and analyze, we see this is a grinding zone on the white grinding zone on the inner side, but when we have a chipping a defect, so this could be a failure origin, but once we really analyze and we see the twist hackles here, the arrest lines there, the wake hackles and all the hackle lines here, we can actually trace back the fracture event up in this region. And in the end, it was a wetting problem here in this. Of course, it's a problem of the tip here. This is certainly not what you do with a ceramic material, but also the wetting problem here, the pores around the tip, they were responsible for fracture of this bridge. You can use fractography in a quantitative way. Let's say you wish to know the level of stress that was necessary to fracture the compound. So we go back to the very simple equation from Irwin, where he relates the fracture toughness with the critical defect and the fracture stress. In that way, that the defect is increasing, the strength is decreasing. And if you wish to increase the strength, then you need to decrease the defect size. So this is very common for all of us as mechanical engineers, of course, but we can use it in fractography. We can measure a defect at a surface or an internal defect. And we can say there is a shape factor, that the Y is the shape factor. Here is the Y, sorry, I haven't mentioned that. Geometric factor is the Y. And this has a different geometric shape for a different ratio of C, extension C to depth A. So we need to modify or adjust and see on a fractured surface how we categorize our fracture origin. And then we can go further. We can see, this is an example, what we did on a fractured crown. It's just the fracture origin shown. This is here, and we measured the fracture size. And from the fracture size, you can calculate kind of, I won't say calculate, but estimate the level of stress that was necessary to drive the crack through the material. So this is assisted, of course, by profilometric techniques. It's also three-dimensionally measured. And this is another example of what we did. We have seen this is a crown, the margin of a crown down there. And you see not only the crack that is starting from down there, going up to the cervical part of the crown. But there is also a shift of the two surfaces, and this is an indication there is something here, 20 micrometer shift in the material. This is an indication of residual thermal stress that might emanate from different coefficients of thermal expansion from the veneering porcelain to the core material that creates residual stress, and those residual stress are creating the defect in the end. We can further, once we retrieve such a piece from a broken crown, we can investigate on the fracture origin. We can add analytical features, and we can say, okay, there is something in the material that should not be. There are heterogeneities, so the reason for failure is easily located. Then you can see where is this material coming from in the process, and then you might recommend for any improvements in the dental technician's process. This is an example, sorry, that should be animated. So in the background, you see a chipped structure here. This is the visual inspection from the clinical image. So this one is chipped, and this was one thing that happened, let's say 10 years ago, very, very often, when dentistry switched the core material, here's the core material, from metal core materials to zirconia, with a material having a completely different thermal conductivity than metals, and then by veneering in the same way as the metal reinforced crowns, we in the beginning created a lot of residual stress at the interface of such a crown, and that led to a high incidence of chipping off the veneering material. This is very well documented in literature, and many clinical studies have shown this fracture incidence, this chipping incidence. And this is an example that from a visual inspection or from a visual finding, we can go deeper and investigate and research into the residual stress state in a material upon the processing parameters, upon cooling such a structure from the sintering temperature. And we did a lot of research, not only us, but a lot of groups that did research on this chipping incidence, and we found that cooling temperature, for example, is one of the major factors controlling the residual stress profile and the chipping incidence. Another example of how you can use fractography, very easy. This is a YouTube video that you might search for crystallization firing of such crowns. This is a glass ceramic material that is fired in a dental furnace. This is the crystallization firing, and upon cooling, opening the oven, it fractures very spontaneously here in the middle of the crown. And this is certainly not desired from a dental technician. And this is a visual finding that led us to the question, so in the end, how is the material consistent? Where are those stresses? Of course, stresses account for the fracture event. There is no external force acting on this crown. So what type of stress is really built up in the material? When we came to the conclusion, there is a lot of zirconia in the initial material, and upon crystallization, the zirconia is enriched in the glass phase and produces changes in thermal expansion. And the role of zirconia in the residual glass is one of very basic scientific questions that we are currently investigating on. So it's a tool. Fractography is a tool that we used for our research in order to go deeper and understand what's going on in the material. To show you a last example, we performed a retrospective analysis of almost 35,000 CAD/CAM or ceramic restorations, and we retrieved those databases from a milling center, and those milling centers, they produce hundreds of restorations a day. And we got the database over 3.5 years, and we investigated. So this milling center sends to the private practice, and once there is a failure or a fracture or any complaint, it goes back to the milling center, and we investigated on the complaints and analyzed statistically, of course, and then also fractographically in order to see what's going wrong. There are mainly, over the 3.5 years, there are mainly bridges, crowns, onlays and inlays, and of course, different materials. The glass ceramic materials, the lucite reinforced material are for smaller restorations with a lower masticatory load involved, and the stronger materials, monolithic zirconia or veneered zirconia, or a cut-on version of veneered zirconia that are used for bridges and for crowns, for example. We retrieved those 35,000 cases, and we did a Kaplan-Meier survival rate, clinically speaking. So for crowns, we can say, okay, monolithic zirconia is the strongest material, quite clear, and the weakest material has the lowest survival rate over time. If we do this with bridges, which are much more loaded, then we see that those veneered versions are less fracture resistant than the monolithic version of zirconia. The survival rate drops with time. So this is a finding that we established on the basis of CAD/CAM manufacturers, standardized manufacturing procedures, and we further analyzed in order to see the lifetime. So we can now do some type of lifetime calculation for those materials, for the crowns and for the bridges. So these are the failed clinical restoration. And then we can say, okay, we have a certain lifetime expectancy of a material, and this lifetime expectancy might be different once comparing the materials, and we can go even further in order to correlate those data with our with pure crack growth studies on those materials, with degradation and fatigue studies on that material. All right, those were examples from the field of dentistry, which you might think of, or you might transfer to other fields of interest. And in the end of my talk, I would like to introduce some of the experience we collected over time with fractography. So the one thing I wish to share is that cleaning of the fracture surface is of key importance. If you don't clean a surface, you don't see anything on a surface, and it very much depends on the material you have. A glass ceramic material, for example, is etchable with hydrofluoric acid, so you modify the structure. This is certainly not recommended for silicate-based ceramic materials, but is certainly harmless, at least in a low concentration, certainly harmless on a zirconia surface. It's the other way around, that phosphoric acid, for example, reacts, the phosphoric group in the phosphoric acid reacts with the zirconia surface and contaminates the surface, but on the other side, you can use it for cleaning of silica-based ceramics. So every material has a certain resistance, and there is a list. Let's say I won't go through all the solutions, but there is a list of mainly alkaline or acidic or tensidic or alcoholic amphiphilic cleaning agents with different pHs. And those cleaning agents, they are used for removal of, and this is again important for you as researchers, you need to know where your failed part is coming from. So you need probably to remove biofilm, blood, saliva, any type of organic remnant on the surface. You have hydrogen peroxide or sodium hypochlorite, EDTA is a bit slower than sodium hypochlorite, but this can be used for cleaning organic remnants. At some point, like in dentistry, you have a contamination or a modification of dentin or the collagen layer in dentin, so you need to be careful using those materials on a surface that involves dentin or organic parts of the dentin. Then inorganic remnant removal with acidic or alkaline removals. This is very much recommended. Phosphoric acid, for example, is very common in dentistry, so we use it for cleaning purposes, but it's also etching the dentin and enamel structure. So we need to be careful. On a ceramic surface, it's much more recommended. Then we have bacteria, viral cleaning. There is disinfection necessary, probably before we receive any part from the clinical application. In some point, in our case, we fix our restorations with cements, water-based cements or adhesive cements. We can remove them with alkaline cleaning solutions. Then we have the typical cleaning solutions that we use in dentistry, which the dental practitioner uses in dentistry, like water and air, ethanol, which is not critical, intraorally. We have some others like silicone oil removal that is necessary when we are using silicons for impressions in the mouth. So we also probably have contamination of surfaces with silicone oil. All right, so cleaning is one thing that is really necessary before any inspection of a surface. And then there is another thing that is very unique in dentistry. This is the replica technique. Probably you already use it, but this is one thing that is developed not originally, but has been optimized for the use in dentistry. Those type of impression materials, so a stronger one that keeps an impression in place, and a lighter one, a more flowable version, a low viscous version, that is really copying the surface by making an impression. So we clean a fractured surface. On some point, we have a crown that cannot be removed from the mouth, or just a minor chipping that cannot be removed, and we want to inspect. So we make an impression and can see on the impression what's going on. So we have to clean our fracture surface, and then we have those trays here, that's so smaller trays. We have the putty version, so the stronger one that we put in there. We put it over the fracture surface and we cure it. It takes, I think, 1 to 3 minutes to cure probably. And then we cut off some of the parts and fill in the lighter version of the impression material also on the fracture surface in order to eliminate every type of air inclusion or bubble. And then we make an impression. This is the impression here. Then we make such an impression, and this impression can be can be filled with a replica material, a very high precision replica material. This is just one thing we use in dentistry, but there are several others on the market, cold curing materials that are not shrinking during setting. So we use this one here. We use a device that allows for pore-free replication. So this is a pressure vessel. You can also use vacuum chambers. That is also necessary. And then with this impression, we create such a replication of the clinical situation. This is another example of a glass rod that we replicated. This is much easier because it's not intraorally used. We could also inspect the original, but we can also do replica. And then the question, of course, arises of the quality of such a replication, and can we see the fine features we are actually wish to see, and in order to analyze on the surface. So you see a picture here on the left, that is the original. It is an edge chip on a glass rod. You can see the surface of the glass rod, and you can see the outline of this chipping defect. You can also see some finer markings like twist hackles here, or here there are twist hackles. Of course, coarser features on the surface at this type of 500-fold magnification at this scale. And if you do, of course, properly, needs a bit of training. And if you do a replica that is nice without any pores or bubbles, of course, you have some modification of the surface. It's not that smooth like this glass surface here, but you can see the major features that are in the same way on the original. You can see it on the replica. You can even see the small hackle lines, the small twist hackle lines, probably some of those hackle lines, but of course, in some point, you are limited. But this is the only way once it's clinical and you cannot retrieve the specimen directly. In the end of my talk on fractography, I wish to introduce you on a few slides an organization that we founded in 2014. It's called Fractal Forum International. This is our website. And we are doing fractography and fractographic education in dentistry, but can also be extended to other fields of biomaterials research. This is the website. So we are having under activities, we are having a training course, 3 days training course on fractographic approaches. And we also have a list of relevant books on fractography, a list of relevant international standards that are used for fractographic inspection. And we have a list of publications, of course, only in dentistry. But if you are interested, go to the website and see our activities. There's a gallery of previous meetings that we had. This is the last one in 2019. Before the pandemic crisis, of course, we cannot do a hands-on course through a webinar or online. This is not possible. But this is our last course in 2019, and some images, how we use the microscope, how we train people, how we interpret images, and how we create some of the simpler experiments, and how we really do our course there. This is the page on the books. There is also the book from George Quinn that is recommended for download. And in the end, I, of course, need to say that this is not my initiative. I'm just giving the webinar, but this is an initiative of a whole group. And I wish to thank, of course, all the sponsors that are supporting our work. And in particular, Susan Scherer, she is very much involved. She's a good friend in fractography from the clinical fractography side. George Quinn, who is, of course, our mentor in any type of fractography techniques and background. He unfortunately retired already, so we learned a lot from his experience and a lot from his knowledge and enthusiasm into fractography. Sven and Jose, two other clinical colleagues that are very much involved in clinical fractography, and Remnant, colleague of mine from the lab side, from the in vitro side, and experimental approaches to fractography. So thank you very much for your attention.
Thank you very much, Uli. Now we have a couple of interesting questions, and I may have a couple more in my mind.
All right.
So from chat, we can see 3 or 4 questions. And the first one, what are differences for fractographic analysis when looking at non-crystallized materials, such as most polymers, less brittle, I think it's meant. And this is very important question because a lot of our material are resin-based.
Yeah. There is a knowledge necessary on the type of material you investigate. Of course, the first step would be to see from simple, I would say, bent bars, for example, to see how a fracture surface looks like. Of course, if you have a coarse structure, like in a filled resin composite with fillers inside, you get a coarser fractographic plane, a coarser fractographic feature. You also have polycrystalline ceramics like zirconia, which have very unique features from the crystalline side, or glass ceramics with elongated crystals. They certainly have specific features which you need to be aware. I mean, fractographic inspection can happen on different levels. So on a microstructural level, it's very difficult because the features are interfering with the fillers in a material, or the crystalline or non-crystalline parts. But on a macroscopic level, you of course have those features. You have those, as shown, those galvings, those wake hackles, compression curl. This can be done. It's more complicated than in glass, and glass is the most easiest material for brittle fractography, but it can be done on those materials as well. Needs some knowledge.
So meaning that you are looking at separately fillers and separately resin matrix, for instance, or polymer matrix.
Yeah, can be done.
Yeah,
can be done. It depends also on the brittleness, let's call it brittleness of the structure, because polymers tend to be more viscoelastic, and they create striations on a surface. And a ceramic is purely linear elastic. So they have different features. So the knowledge of the material is very important to investigate on a surface.
Yeah.
I have shown a picture called galvings. Those galvings are very likely to emanate from a filler particle, for example. This is a feature you don't see in glass, for example. Maybe if you have some heterogeneities in the material, but if you have in a pure glass, you don't see this feature. You see it on a two-phase material like a filled polymer.
Yeah. Then there is question that when analyzing clinical situations that involve multiple materials, dentin, cement, ceramic crown, what signs would point to the origin of the original stress being outside of the restorative material?
All right.
Complicated issue.
This is complicated. This is like how to do fractography in total. So you need to start asking the dentist, how did you treat a patient? What adhesive agent did you use? How did you treat the surfaces? Then you need to investigate on the technician side. What are the materials you used? What is your firing program? All these aspects are important. And then you need to see the occlusal situation in the mouth. You see the cusp. Which cusp is involved? The mesial, the distal, the lingual cusp, which one is involved? And what is the antagonist at this specific cusp? So let's say if you have an implant and a zirconia crown, let's call it a worst case scenario, as an antagonist, you certainly have a completely different loading situation on a failure origin than you have with a different scenario or a natural tooth as an antagonist. And then you need to see the several interfaces, the several surfaces as a compartment, and you narrow down, you come closer to the event, and in the end, hopefully you find the fracture origin. It's not always guaranteed, of course, but you can narrow down the effects, you can make up the history of the whole thing, and then hopefully you get some information that are useful for your research.
Good, and then there is a question that does the bond between zirconia and veneering material have a relation on fracture strength and the type of fracture?
All right, this is a question probably towards what happens at the interface between the zirconia core and the veneering porcelain, because this is one of the major aspects in this chipping issue I reported on. I said there is clinical chipping going on veneered zirconia, and this is probably a question of the interface. Our investigations, if you cross-cut such a crown, in most cases, I would not say in all cases, in most cases, you see a layer of veneer on the interface, on the zirconia, a layer of veneer that is indicating this is not an issue of bonding between the two materials. This is an issue of residual stress. There is a compressive layer in the veneering material, and this compressive layer is still on the surface, and when the stress profile, the stress gradient moves into the veneering material, there's a layer where the veneering material chips off. So the interfacial bonding between glass, veneer, and zirconia core is not an issue. It's not a clinical issue. It's the stress in the material.
Good, thank you. That is very interesting. Certainly we can discuss this some other time more in detail.
All right.
But of course, stress is by the end causing those failures and fractures. But then there is very interesting question. There are a couple of them, but I catch one. Do you have any comment on the rule of dentin enamel junction on the fracture of tooth structure? Can we simulate somehow this kind of dentin enamel junction with our restoratives or restorations?
Yeah, well, this is a complex interface. The dentin enamel junction is a complex interface. I mean, this is a growing interface from amelogenesis when the enamel develops from the dentin. It's a growing interface. So this is very well interconnected, and this has a wonderful toughening effect that the enamel and the enamel structure, the enamel prisms are oriented, and there are regions in the enamel that are decussated. They are kind of changing their directions. They are creating a three-dimensional network, and with this network, they are reinforcing the enamel. And this is why you see cracks in your teeth, and they don't just break off. The teeth are not breaking off. because the enamel actually shows a very, very prominent R-curve effect. So the increase of the resistance of a crack into the material is very prominent. And this actually reinforces the enamel.
Good. Now I think there are some more questions, but they are almost of topics you already covered in these previous answers. I have one in my mind, which is referring to the very first slides of your presentation of these laminated glasses and safety glasses of a couple of layers of glass and a resin-based adhesive between them. In my mind, they are looking very much the same like our present adhesive restorations. Glass ceramics, for instance, adhered with resin layer to brittle dentin or enamel, and then that entity is more or less like a laminated glass. Can you see analog from engineering perspective of this kind of structure, what we are building in the best case with good adhesive interfaces to both sides, with the glass plates which are used in cars windscreens, for instance? And if so, what is then going to be the role of thicknesses of these layers? In window glass or safety glass, you have quite thin layers of glass adhered together. But in our restoration, we can have quite thick glass ceramic layer underneath. We may have, in the best case, mounting. So how would you?
Yeah, I mean, this is an interesting question in glass production or window shields, for example, they use different layers, but they have a polymer interface like we have with our adhesive in between two glass layers in order to prevent upon a fracture of a window shield, in order to prevent the crashing and the damage that can emanate from the broken pieces. I mean, the problem in the mouse is that we cannot chemically, I don't know, or thermally strengthen our materials, because once it comes to a fracture event, there's a lot of energy involved. This layer in terms of chemically exchanged or compressive layers on a restoration, they have so much stored energy in it. Once it comes to a fracture event, then it's harmful in the mouse because it has a lot of energy involved. And surfaces are degrading over time, either from the dentist when he makes occlusal adjustments, or from the patient when he's going home and he's biting, he's clenching, he is bruxing, or just eating. So those defects on a surface, they are increasing. They are into the material. They are increasing and leading to premature failure of a restoration. Once we have a very, very thin hardened surface of such a material, then probably upon a drill inspection from a dentist, you go through this layer and you fracture the veneer layer, I'd say.
Yeah, in fact, what is one of the questions here, is there correlation of fracture pattern of ceramic crowns with type of occlusion bite for and thickness of the restoration? I would add to this question or comment also that to what extent we can actually compensate brittleness of the material by the good adhesive layer to the underlying dentin and enamel.
You mean a damping of a crown, let's say, on through the support layer from?
Yes, if the layer is good in quality in terms of adhesion to both sides. So
I mean, to a certain extent, because it's not always the stress that is leading to fracture, it's also the strain. So the strain is very limited. I mean, occlusion, if your dentition is in occlusion, there's only limited strain that is applied on a surface. And due to the much higher elastic modulus of ceramic materials, for example, we have a much less strain that is involved than, for example, in more elastic materials like the adhesive or the support. Once you support a restoration with a resin composite, for example, has an elastic modulus of 15 or 20 gigapascal, ceramic has 100 or 200, depends on the material. So the ceramic itself is the stiffer material, and once there is force coming on the surface, then we are having a problem because the support is only of limited damping behavior for this brittle structure. This is the reason why we need a certain thickness of a restoration. Once you go, you cannot go down with a ceramic restoration to 0.5, 0.3 millimeters. It's not possible because then the fracture incidence is very much increasing. So the support is on a certain point is limited.
Yeah.
Of course, if you think of the whole tooth compartment, and if you put a whole layer that is kind of supporting the whole crown, that is something different that might help. This is what people do on implants, for example, because implants, they are screwed in the bone, they are fixed with the bone, either titanium or zirconia implants, and then there's a strategy to put a low modulus crown material on top of an implant in order to increase the damping in between the dentition.
Very interesting. Very interesting. We may need to have another seminar of fracture behavior of materials, not only fractography. Would it be possible, Uli?
Yeah, let's see. Of course, we can continue this discussion. I would be happy, of course.
Yeah, because I think there's a lot of things to be discussed, because dentistry is adhesive dentistry. We are using brittle materials, highly cross-linked polymers as a composite. So they could be interesting to look at these.
Yeah, true.
Multi-layer structures more in detail.
True. Yeah.
But anyhow, now we are ready to, I think, close the webinar. There's a lot of thanks in the chat, and it's my privilege to thank you also very much, Uli, and then of course Markus and our journal JMBBM team, publishing team of the Elsevier, that we had chance to have this kind of nice and very important webinar of this topic. And certainly, as said, this will open a lot of new questions which should be looked at more in detail in the webinars and the meetings, and then published papers and submitted papers, which we are of course inviting a lot to have in our journal. So if there is nothing else, would you like to tell something, Markus, to the very end?
Yeah, no, I just want to thank you both. Thank you, Ulrich, for a really amazing webinar. I enjoyed it tremendously. And Pekka for moderating it and dealing with all the questions. We had a lot of them, and I agree we should do another one on dental materials. I think that's a great topic, and we will plan for that in the spring. As always, we're looking for speakers. So if you have ideas, you can either self-nominate or you can nominate someone else. Send the ideas to me, and we'll be planning the spring webinar series, probably starting December. We have our last webinar coming up in December. That being said, I want to thank you all. I know we went over a little bit, and I appreciate everyone staying on. We had a great audience, very engaged audience. And I wish you all a great afternoon. And as Pekka said, please submit your papers to JMBBM. We're looking forward to having them. I think we're breaking another record this year in number of submissions, so thank you all. And particularly, I always like to thank the reviewers here on this webinar, because many of our community are, of course, attending and also reviewing papers for us. So thank you all for the hard work you're doing and the help you're providing the editorial process. With that, I wish you all a great afternoon or evening, and I'll see you soon. Thank you.
All right.
Thank you to all.
It was a pleasure. Thank you.